Dymola is capable of simulating dynamical systems over a wide range of domains, including mechanics, electronics and thermofluid analysis. The package browser to the left shows all the available building blocks. Dymola contains multiple packages for simulating mechanical systems. Among these are the one-dimensional rotational and translational packages, which have built-in models for gears, brakes, rolling wheels and bearings, in addition to basic components such as inertias, springs, and dampers. We will focus on the more general three-dimensional multi-body package, which contains general rigid bodies and joints, and interfaces to connect between the one-dimensional packages. Now, let's build a simple mechanical system using these components. Our goal is to construct the crank system shown below. Joints and connections are shown in red, and the remaining objects are rigid parts. We begin with inserting a world component through a drag-and-drop maneuver. It defines the direction and strength of gravity, as well as the global coordinate system. We now insert a rigid cylinder as one of the parts in the system. The size and position of an icon are easily manipulated. Likewise, an icon may be rotated if desired. By double-clicking on an icon, we can set the properties of a component. Here, we define the cylinder's geometry by specifying the position vector between its end faces, as well as its diameter. Density is left at the default value. When entering a quantity, we may choose the unit in which to specify it. Unit conversion is conveniently handled by Dymola in the background. There is also support for custom user-defined units. Now, let's insert a revolute joint to connect the bar to the fixed origin. Again, we double-click to edit its properties. We specify the axis of the joint in the dialog. Let's now connect the present parts. To connect two components, we select a frame on any component, displayed as a rectangle. The connection is finished by dragging it to another frame. We will add a second bar to the model, again using the cylinder body class. After rotating the newly added bar, we set its orientation and diameter, and leave the density as is, just like earlier. We now add a prismatic joint, which constrains motion onto an axis. The axis of the prismatic joint has to be set. The end of the prismatic joint shall be fixed, but not to the origin. To fix it to another point, we add a fixed translation component representing the point's position vector. The position vector itself is then entered in the dialog. It's also excluded from post-simulation visualization, since it does not represent a physical component. Now, the newly inserted parts are connected in the same manner as earlier. The mechanism will be tied together using a universal spherical joint, that is a coupling consisting of a universal and a spherical joint, connected by a rigid rod. After flipping its icon, we edit the properties of the joint. The position vector between the universal and spherical joint is specified, representing the rod. The orientation of the universal joint is also defined here. By connecting the universal spherical joint to the nearby bars, the system is completed. Now that the model is assembled, it needs a set of initial conditions. Suppose that we are to prescribe the angle and angular velocity of the revolute joint, and the extension of the prismatic joint, whereas the length of the connecting rod is unknown. Initial conditions are set in the same dialog as component parameters. The angle and angular velocity of the revolute joint are now specified. Now, let's specify the initial extension of the prismatic joint. And finally, to have the rod of the universal spherical joint assume the correct length, we enable the flag compute rod length. The model is now ready to run. But first, let's save our work. A model can be saved just as any other file. If we desire to examine a component more closely in the model, we can do so at any time. Open class takes us to a diagram view of the component. While viewing a class, we can conveniently switch to its coding layer or its documentation to retrieve desired information. By using the tabs feature, we can instantly return to viewing the model. So far, we have demonstrated how to build a model of a simple crank mechanism, though Dymola supports general constructions of arbitrary complexity. This robot arm is an example of a more complex model, retrieved from the examples library included with Dymola. Let's go back to our model to simulate it. We will switch to the Simulation tab, and then enter the simulation settings. We will set the simulation time to 4 seconds. From here, one may also change the solver algorithm and solver tolerance. We finally simulate the model using the Simulate button. The animation window provides a visualization of the model. Let's adjust the view, and then play the animation. The motion of a part may be tracked by selecting it in the animation window. In the browser on the left, the components of the model are listed. Expanding an item shows all quantities associated with that component. We may plot a variable, for instance the extension of the prismatic joint, by checking the box next to it. Keep multiple boxes checked to plot several variables at a time. Suppose that we're interested in studying the effects of different initial extensions for the prismatic joint. We may try a different initial value simply by editing it in the variable browser, and clicking Simulate once again. Note the different geometry in the animation window. The connecting rod is significantly shorter, and the prismatic joint is extended farther. We may again plot the extension over time, and note that the curve has a different appearance.